Welcome to the Hilbert versus Gem action Smackdown. In one corner we have the Hilbert action of general relativity, a very venerable opponent. And against it we have the newcomer, the Gem action unified field theory. Actually, it's composed of an even older and more venerable component, and that would be the Maxwell equations, but there are also these terms with lots of pluses in them that I hope may do the work of gravity. And we're going to knock both of these proposals down a notch, and may the better proposal win. Gravity is dynamic geometry. Einstein realized this just by thinking about it. And we have subsequently done a lot of elegant experiments which show that in fact that is the case. What Einstein wanted was to mimic Newton's second law, the F equals ma sort of thing. But he wanted to do that with a metric tensor, which is a way to measure how far apart things happen to be. And by having a second order differential equation, he would have a dynamic metric, a dynamic ruler essentially, for measuring things in space-time that would change because of mass. That was the core idea. So he turned to his math buddies and said, "What can you give me?" What he got was the difference of two derivatives of a metric. The action is the integral in curved space-time. That's what most of those terms are in the action, the machinery for integrating in curved space-time. The real heart of the action is this R, which stands for the Ricci scalar. The Ricci scalar is a contraction of the Ricci tensor. The Ricci tensor is a contraction of the Riemann curvature tensor. The Riemann curvature tensor is a comparison of two paths by taking the derivative of one connection and comparing it to another. A connection, if you assume it's metric compatible and torsion free, is the Christoffel symbol of the second kind. The Christoffel symbol of the second kind is a contraction of one metric with the derivative of three other metrics, and so it's essentially the derivative of a metric, and it's just the difference of these two. Very simple, isn't it? So what Einstein got was the derivative of two nearby paths. Now, what are the consequences of that? One of the most important consequences is that energy is non-local. If you choose any point in space-time, then you could choose a coordinate system such that energy was zero at that point. Now, you cannot do that for a volume of space-time, but you can transform energy away for a point, and so therefore energy is non-local. Today that is accepted as a feature, and a very deep feature indeed. But it makes gravity different from all other known forces in nature. And that's why people who work in gravity generally talk amongst themselves. But if that difference is actually wrong, I think it's a deadly bug. It may be the technical reason why general relativity has resisted all efforts to quantize it for over 80 years by the brightest people on the planet. So I think we must avoid using the Ricci scalar R and all of its friends, the Ricci tensor, the Riemann curvature tensor. But we must get back to Einstein's initial goal, which was to come up with a constraint on the metric which requires one and only one derivative of a connection. So here is the Gem unified field action, made up of Maxwell's action along with other components. So what's wrong with this? Well, this is kind of embarrassing to even work on, because Einstein spent over 30 years and he completely failed. And he would admit that he failed, but he kept on going anyway. And it's embarrassing to work on something that is just that darn hard to do. And certainly what is written on this page must have been tried before. If you have a theory that's like EM, and EM has like charges that repel, then there's no way you could make this a theory of gravity, because for gravity, like charges attract. You miss that basic property, there's no reason to talk any further. And Maxwell's equations require that you provide the metric as part of the background mathematical structure. The whole point of general relativity is you end up with a differential equation whose solution, based on the physical situation, dictates what the metric is. So I think these are great reasons why to just dismiss this proposal and work on something else. But we'll look into these things just a little further. So has this been done before? This is the Maxwell source equations. So of course this has been done before. This is the best field theory in all of physics. But let's just kind of go through the exercise. I happen to be using quaternion operators because I'm a specialist in that, but that doesn't matter too much. What you basically end up with here is the b squared field minus the e squared field, and that makes up your Lagrangian. So here it is in all its various component parts. And what you now do is take derivatives of that with respect to all these different potentials. So there are 4 different derivatives of 4 potentials. It's 16 in all. And to help you along, I've isolated all those things that have a phi in it. And when you do this sort of exercise, you get Gauss's law. When you do this for in the A1 direction sort of thing, you end up with an Ampere's kind of law. And you do that in the second direction and then third direction. And it is in all its glory. If you've ever played a game called Missile Command, it should remind you of that. And there's our summary statement. And so, yeah, this has been done before. Now, what I'm doing for the gravity terms is a little bit different. And by little bit, on that first line where those blue turquoise colors are, is where I've switched a sign. So there are only 2 sign flips that really come in here. And what do? Well, the idea is that we've got, say, the time derivative of A and the gradient of phi. And we ask the question, what should be the relative signs between these two? And we say that the complete answer is that they should be both the same as it is in EM and different, as I hope to show for this proposal dealing with gravity. And we do the same thing for the curl, because the curl is also the derivative of 2 components. One of them, they're different from each other, and that ends up being the B field of EM. And I hope to show that if they're the same sign, then that makes them this this symmetric B field, symmetric cross product, I call it actually, that has to do with gravity. So after we make those 2 changes up on that very first line, everything else becomes automatic. Everything about this is structured exactly the same. We get this square of the B field, small b field, minus the small e field. And those show up as 12 different signs when we write it out in terms of its components. And we do the same exercise of taking 16 different derivatives, putting them all in the same spots. Now here we can see something very important, because we can see Newton's law. And we know that's a darn good law, and we know that darn good law has a specific technical flaw, and that is that changes in the density had to propagate instantaneously. And in fact, you can go from that one observation, if you're somebody as good as Feynman or Weinberg, and go directly to Einstein's field equations. But that is not necessary in this case, because there are time derivatives of A. And so that whole raison d'etre for gravity is not there, for general relativity is not there. This will be able to handle changes in time. And we do the same thing for A1, and we get a different law. It's very similar, just using the small e and small b field for A2, for A3. Our summary statement is right there, and I have yet to see anything like this. I saw in Mrs. Thorne and Wheeler how they tried to just tack on a time derivative of phi, or they tried to use an antisymmetric tensor. Those didn't work, but that doesn't mean that this doesn't work. Uh-oh, double negative. Now, you must be able to show that like charges attract. What I didn't recognize for a number of years was that the vector coupling term, which is just JA, actually is part of this discussion about whether like charges attract or they repel. Because we know that for the transverse current, like charges repel because it has spin 1 symmetry. And I hope to show you that actually it also has the spin 2 symmetry. Now, I was told this by someone who pointed me to chapter 3 of Feynman's book on gravity, because he worked it out there. And I can't expect to show where Feynman was wrong. What sometimes, or I should say very rarely happens, is you can show that someone else's analysis was incomplete. They didn't think through all of the calculation, and it's that error by omission that I hope to indicate right here. So you start with the coupling term, which is, as I said before, is just JA. You take the Fourier transform of that potential to get a J and a J prime along with that K squared factor. We expand this, and this is the term that shows up in the Lagrangian. But what we need to do is analyze the phase. So we look at all 4 possible products of these 2 currents, and what we get here is exactly what Feynman calculated, which is these what I call this perpendicular current. Basically, it's the curl sort of thing, and those 2 don't work together. And so, since they don't work together, they're going to take 2 pi rotations to get around. And since they take 2 pi rotations to get around, they have spin 1 symmetry, and their like charges repel. But what Feynman does not do is he does not comment at all about the rho J term. And you can see that those 2 actually work together. Since they work together, that has spin 2 symmetry. And since it has spin 2 symmetry, it means that like charges attract. But even more so, it means that this attractive force will actually apply to photons. This is an important quality because a spin 0 field does not have the ability to bend light, but a spin 2 field does. So I think this error in omission may indicate how the coupling term for a vector coupling term can do like charges attracting. Now the third issue has to do with the metric being a solution to a partial differential equation. And I hope to show you that the metric is a solution to an equation that does not use the exterior derivative. So what is an exterior derivative? Well, that's what we call this derivative that is used for the EM field strength tensor, where you've got this subtraction and you've got an antisymmetric tensor. Now, since the we use the definition of a covariant derivative, which is just a normal derivative minus this connection. And if this is symmetric in the lower indices as it is, then these two cancel each other out. Now we can understand why the Maxwell equations must have the metric supplied, because this thing that could give us information about how the metric changes is eliminated in that step. Now I also have in my action something where these two are added up together, and so when we use the definition of a covariant derivative, we see that they add up. And the field equations are going to be a derivative of this thing, and because we take a derivative, we end up with a derivative of a connection. And that was exactly what Einstein wanted to get at so many years ago. So we are going to show here that the exponential metric is a solution to what I call General Gauss's equation. We're going to assume that all the derivatives of A are going to be 0 because A is constant, neutral, non-spinning. And you might say, well, that's very, very simple, but that's the exact kind of thing that you need to assume to get the Schwarzschild metric of general relativity. And here is the exponential metric, and I think this is manifestly beautiful because it has all those exponentials, and exponentials are in important laws of physics. That's not an accident, by the way. It is the way nature appears to work, because the exponential, when your exponent is really small, is basically almost 1. And then it does small variations around 1. So physically, what we're saying here is that space-time is almost flat, but if you take a small step away from flat, you're going to get into simple harmonic motions sort of situations, like the Earth going around the Sun for 4 billion years, or a ball wanting to oscillate around the center of the Earth, even though everything else gets in its way. So we have a kind of a physical sense of what that metric is trying to do. But does it solve this, what I call General Gauss's equation? Well, we use the definition of a covariant derivative and get these derivatives of the potential in there, and since we've assumed that A is constant, they drop out. That leaves us only with basically the gradient of a connection, and the connection is these 3 derivatives of a metric. Fortunately, 2 of them bow out. One of them bows out because this is a static metric, it doesn't change in time, and the second one bows out because it's diagonal and none of the terms survive that sort of thing. And so we just have one term to analyze, and lo and behold, it ends up looking just like something Poisson would know about. Now, some person I remember said, well, you're only constraining one of the terms of the metric, but that's because I only worked with one equation. The Gauss's law thing is really a statement about G00. There are other constraints. For example, you had to pass all the weak field tests of general relativity has already passed, and this will do that because every term in the metric to first order parameterized post-Newtonian accuracy is the same as the the Schwarzschild metric of general relativity. So it's not going to have a problem passing all the tests that have been done so far. It's also a proposal that is actually simpler than general relativity. One of the problems with taking general relativity and adding on something and making it more complicated is that when you take that step, you allow things like the gravity waves to be a result of a dipole. In fact, this metric is known as the Rosen metric in the literature, and it runs into that problem. But in this case, that's not an issue because the proposal is simpler because we only have the derivative of one connection, not the difference of the derivative of two connections. So, to review what we've done, we have underlined a problem that has been known for a long time in general relativity, and we acknowledge that most people don't think it's a problem, but it's an interesting thing to think about. But it certainly is possible that that interesting thing to think about is actually a very serious problem. And we've looked at three different issues in this proposal. Has this been done before? Well, when you look at the details, I don't think so. Can we have like charges attract? And if we do a complete analysis of the spin coupling term, the current coupling term, we can see how like charges could attract with a spin 2 particle. And finally, we've seen a very specific metric applied to a very specific a differential equation, and it is a solution of that equation, and that looks physically relevant. So you get to decide, but I think there is some good hope for the GEM action. Thank you very much.